Hello everyone, my name is Yoav. I did my PhD in physics in Envy Centers at the Hebrew University, finished about a year and a half ago, and I've been working at quantum machines ever since. And I'm going to tell you about some interesting projects that we have going on that are enabled with the use of the OPX system. So what's the agenda? I'm going to talk about adaptive thresholds for nuclear single-shot readout, active initializations of nuclear spins, and real-time adaptive Bayesian distribution. Before I go too deeply into that, let me quickly talk about our platform. So we have the quantum orchestration platform, or the OPX, and the idea is it's a dedicated hardware meant for quantum control, and it allows you to run sophisticated algorithm quite easily. And how do we do that? So using it is very simple. It's using a high-level language. And if you want to play a pi pulse on the memory, then you simply write play a pi on your memory, nuclear spin, for example. If you want to do a measurement, you want to do time tagging, this is how you would do it. You have variables that you can use in real time to do classical operations. This is how we can do Bayesian estimation, for example. And we have various other stuff. We can change the frequency, the amplitude, we have control flows, and so forth, and all of that in real time. Let's delve into the more interesting things. So the first thing I want to talk about is adaptive threshold for nuclear spin. Okay, so what's the system? We have an Envy center, that's the electron spin, and then it has, for example, the N nuclear spin. It can also be, of course, a C13 or something else. And the Envy readout fidelity is very low. It's less than 0.1%. But we can use the N, for example, as a memory, or we could just want to read some nuclear spin. So for that, what we can do is do repeated measurements of the nuclear spin with the Envy center. And this was demonstrated a long time ago by Newman et al. With the Envy centers. And on the left, you see recent data from the Lukin lab with the OPX. Okay, so this is generally single-shot readout, but what do we want to do? We want to have an adaptive threshold. What does that mean? So what's the problem? The problem is that we have a trade-off. If we want high fidelity, then we need a large number of repeats. But that means that we have long readout. And this starts to become complicated, especially when you have multiple nuclear spins and so on. The long readout really starts to slow you down and to hurt your overall fidelity. And each repetition that we are doing pushes the two states further apart. So if you take a look at this simulated graph, you see that we have the two states, and let's say we did 2,000 repeats, then we get the graph on the left side, and we have the two states. And if we have a large number of counts, let's say in this graph 75, 70, something on that, we can safely say that we're in the up state. If we have a very low number, 30, then we can safely say we're in the down state. But what we usually do, we do a very large number of repeats. We push the two states further apart until they're clearly separated. But however, with the OPX, what we can do is actually use this information and have a dynamic number of repeats with two adaptive thresholds. What do I mean by that? We simply do the 2,000 repeats. If we see a very large or very low number of counts above and below these two thresholds, then we can stop the measurement and just know what the state is. If it's not, then we do another, let's say 1,000 repeats. The states are being pushed apart, and then we can distinguish them, and we can repeat that until we know at which state we are. So let me quickly show you how the code for that looks like. We have here an assign command, and assign is simply counts equal to 0. Then we have a for loop, so we're doing j smaller than m, so we have m repeats, or until success, until we have the achieved fidelity. Then we have n readouts per iteration. Inside each one, we have a conditional pi pulse. We do a measure in which we do time tagging. And we just look at the total number of counts. We don't actually use here the individual times at which the photons arrived. We calculate what the threshold should be depending on this variable j, and then we compare to the threshold. If we're above one of the thresholds, then we're in the 0 state, and it's true. If we're below, then we're in the 1 state, and again, we achieve the fidelity. Now, this is example for an N15. This can easily be adapted for N13, where it will actually be even more useful. And we already see that using this, we can get 3-time reduction in the number of repeats, or in the total time, the measurement time, for the same readout fidelity. So that's quite nice. Okay, so that's the first thing, the adaptive threshold. The second thing, active initialization of nuclear spins. What do I mean by that? Okay, experiments with nuclear spins usually require post-selection, and that means that if you want to post-select the experiments in which the nuclear started at the correct state. If you have one nuclear, then it's simple, but if you have several different nuclears, then this becomes more problematic. Of course, you can also do swap gates, but usually they don't have very high fidelity, and there's other problems. What we can do, we can actively initialize the nuclear spin. So we do a single shot readout. If we're in the correct state, let's run the experiment. If not, let's run a pi pulse on the nuclear and then run the experiment. And the single shot readout can be actually the last readout of the last iteration. So we don't need to do a specific one. And this is how it would look like in the code. We simply have an if state if the state is in the correct state, and if not, play a pi on the memory. Again, this can be easily adapted to N14, but this is for N15. Okay, last thing I want to talk about is real-time adaptive Bayesian estimation. So as you know, this is already been talked about in this session. Ramsey pulses are used quite a lot to measure DC fields. And you accumulate phase, which depends on the field and the time in which you do it. And the most common way to actually extract the phase or the magnetic field is to use a Bayesian estimation. And this was, again, shown many times. This is an example from the group of Kristen Bonato, in which they showed how Bayesian estimation can be used even without single-shot readout. And this is being used in many labs. I'm sure many of you are using it as well. But what are we doing extra? So we can do multiple things. One thing, we can have adaptive theta. What's theta? Theta is the phase of the second pulse, of the second pi half pulse of the random sequence. And we can be shown that the optimal theta is given by this equation. And you have here the estimated frequency that you estimate in real time. And then you have some argument which depends on the number of counts. This is actually currently being done by the group of Amit Finkler. In Bar, the student working on that is presenting that right after this talk in a parallel session. So if you're interested, you can go and check that out or view the lecture later. And this is showing some nice results. So this is the first thing that we can do. The second thing that we can do is have an adaptive tau, the time at which we probe the Ramsey sequence. So usually you just increase it by a multiple of 2 every time, but you can do it adaptively. And we just had a talk about that in this session not long ago. We actually, once the paper was out, we saw that and got excited. We implemented the code for that with the OPX, quite simple. And we're now working on getting the results and seeing what we can actually do with that. Again, something which we can do in real time, which will increase the performance a little bit. So that's it. If you're interested in learning more about what you can do with the QOP, then we have several nice lectures. You can go and check them out. You're more than welcome to check out the booth at 609. And that's it. Thank you all.